Hello, my name is Tom Nania, and I'm excited to be presenting at this year's Oberlin Acoustics workshop. I look forward to a time when we can all meet again and share our work in person. However, until then, this is the safest and next best thing. I'd like to thank Fan Tao and Joseph Curtin in the Violin Society of America for bringing us all together virtually. I'm a lifelong guitar player turned guitar maker and instrument acoustics researcher. I had the opportunity to play an Archtop in my high school swing band and have been hooked ever since. I am co-proprietor of House of Luthery, where together with my wife Becca, we build carved top guitars, conduct instrument acoustics research, and educate for the good of guitars. I'm also an affiliated scholar with the Department of Physics and Astronomy at Indiana University in South Bend. First, a little context of how this all came to be. I became aware of guitar making as a profession upon discovering the work of a local luthier. I instantly knew this was the profession for me, and I embarked on a path to study the fundamentals of sound, earning a degree in physics. I then enrolled in the Gallup School of Guitar Building and Repair. While at the Gallup School, I read everything I could on guitar physics. David Hurd's book, Left Brain Luthery, and Trevor Gore's work on the contemporary acoustic guitar were both very influential. However, when I went to look up similar work for the Archtop, there was very little and nothing complete. There was a brief interferometry study that concluded more work needed to be done. However, there was a treasure trove of violin acoustics work through the Catgut Acoustical Society and the Violin Society of America. And so I began studying the Archtop, with the publications of Cass and the VSA paving the way. 6 years later, here we are. The Archtop guitar is very much a product and design of the turn of the century and early 20th century innovation boom, with hardly the refinement of the Cremonese violin. The Archtop is designed after violin family instruments, with a carved top and back, often of spruce and maple, originally with a single circular sound hole or oval-shaped sound hole, later with double F-holes. The design of the Archtop guitar is credited to Orville Gibson and his Gibson Mandolin and Guitar Manufacturing Company, with his original patent in 1898. Gibson was located in Kalamazoo, Michigan, and one of their early advertisements read, "The delicate plate graduation leaves the grain layers and fibers in their natural position, free and sensitive, helping to amplify vibrations to their finest possibilities." Gibson hired acoustic engineer and luthier Lloyd Lohr in 1919, and by 1922 introduced the L5 acoustic Archtop. Similar to this guitar here, although this is an L50 from several decades later, the L5 originally was a 16-inch lower bout with double F-holes. By 1935, the L5 grew into a 17-inch lower bout to keep up with its competitors. American music was coalescing in the 1920s. Two genres of music that emerged were country and jazz. Maybelle Carter and the Carter family recorded some of the earliest country music in Bristol, Tennessee. Maybelle Carter played an L5 Archtop. Up north in Chicago in 1929, guitarist Eddie Lang, born Salvatore Massaro, also playing an L5, collaborated with Louis Armstrong on a tune, Knockin' a Jug. This recording is monumental for many reasons, one of which was Lang showcasing the versatility of the Archtop guitar as both a lead and accompanying rhythm instrument. These paradigm shifts in playing style, along with the design improvements of the Archtop guitar, grew its popularity, along with the emergent technology, radio. For jazz in particular, Lohr's design allowed for the Archtop to project and keep pace with the raucous jazz orchestra. Soon, the Archtop replaced the banjo as a prominent rhythm instrument. Around the same time, the upright bass replaced the tuba, effectively transitioning the rhythm section from brass to strings. Meanwhile, in California during the 1920s, George Beauchamp was designing the original single-coil pickup. By 1936, Gibson introduced their bar magnet pickup in the ES-150, played prominently by Charlie Christian of the Benny Goodman Orchestra. Soon, this bar magnet pickup was dubbed the Charlie Christian pickup. The guitar became electric, and its popularity is history. The work being presented, Archtop Guitar Dynamics, is a modal analysis establishing the fundamental eigenmodes and corresponding eigenfrequencies of the Archtop guitar top plate and corpus. This study follows the acoustic shifts throughout the build process, beginning with the free plate and ending with the completed guitar with finish under string tension. The vibrational acoustics of the Archtop guitar were theoretically modeled using finite element analysis and experimentally measured using FFT, and Chladni figure analysis. For each step along the build process, a CAD model was drafted for finite element analysis. A CNC milling machine cut a top and back plate identical to the models made of spruce and maple for experimental analysis. The free plate was analyzed at 3 different steps along the build process, beginning with the graduated top to F-hole perforation and finally X bracing. The braced top was then glued to the sides and back. Measurements were taken of the corpus, and then a final set of measurements after the neck and hardware were attached. Both before and after finish were taken. For this study, a 17-inch L5C style guitar, the C standing for cutaway, was used. The construction of this guitar may be referenced in Bob Benedetto's book, Making an Archtop Guitar. Now, let's begin the analysis.
This is an image of the Archtop top plate CAD model used for finite element analysis. The FEA was performed with COMSOL Multiphysics and Autodesk Fusion 360 softwares. Colin Goff's paper, Violin Plate Modes, guided the FEA experimental setup. The inputted material properties were consistent with the average properties for Alaskan Sitka spruce. Book-matched grain lines were added to the model, spaced 2.5 to 5 millimeters apart. The grain lines represent the anisotropic nature of spruce with varying Young's modulus values. It is important to note the computer models do not compensate for the fact that an archtop plate is carved and not bent or pressed. The effect on results are higher modeled frequency values. However, the fundamental eigenmodes, like the one studied in this work, are primarily determined by the profile of the arch and boundary condition of the guitar shape, along with the average material properties. The finite element analysis reveals the modal shapes. The explicit frequencies were determined experimentally. A comparison of the X bracing for the model and experimental top plate. The plate was carved on CNC to match the dimensions of the model. The top is Alaskan Sitka spruce. Note the cross braces at the top and the bottom of the X. The first set of FEA results are presented here. The left-hand column shows an image of the model used for each set of results. The first model is an isotropic square plate. The physics of such a plate are well understood. The second model is an isotropic rectangular plate with an aspect ratio of 1.25 to 1. This is the aspect ratio of the archtop guitar plate, compared with the 2 to 1 ratio for the violin. Next shows the anisotropic rectangular plate with grain lines. The following model is an anisotropic flat guitar-shaped profile, and finally the arch top plate. All of the models have uniform thickness of 0.187 inches or 4.75 millimeters. The results of the first model, whose aspect ratio is 1 to 1, show the characteristic twisting mode, primarily influenced by the shear modulus, followed by the X and ring modes, dominantly influenced by the Young's modulus. It is understood that the X and ring mode shapes manifest as the superposition of the fundamental bending mode resonant frequencies, side to side and top to bottom of the square plate. Because the plate is square-shaped, these standing waves are the same frequency and, depending on the phase relation, vibrate in the characteristic X and ring mode. It should be noted that the X and ring modes show up in violin plate physics and are the second and fifth eigenmode shapes. The anisotropic nature of quarter-sawn spruce, with grain lines running the length of the plate, has greater long-grain stiffness than cross-grain stiffness, and this disparity, coupled with the aspect ratio of 2 to 1, meaning the plate is twice as long as wide, create the right conditions for the X and ring modes to manifest in an anisotropic plate. As the models progress to become anisotropic and guitar-shaped, the X and ring modes do not show. There is an X mode in the guitar-shaped results, however, it appears to be dominantly governed by the long grain bending mode and arch profile. This slide shows the 3 working steps of the free plate. First, the standard graduation, next, F-hole perforations, followed by bracing. The top set of models are anisotropic, and the FEA was performed in COMSOL multiphysics. The bottom set are the same models, but are isotropic, and the FEA was performed in Autodesk Fusion 360. Again, it is important to note that the fundamental eigenmodes and corresponding eigenfrequencies are dominantly governed by the boundary condition of the guitar shape, the arching profile, and average material properties. The Fusion 360 models show an X-like second mode and a ring-like fifth mode. However, these are not the same X and ring modes of the violin free plate, given the different aspect ratios. The addition of the X brace disrupts the ring shape of the fifth mode according to the results. It should be noted that when the COMSOL models were run as isotropic guitar plates, there is no ring-shaped mode in the results. Here we have the pinned edge results. This combines the models of the previous 2 slides with the modification of a pinned edge. The bottom row represents the braced guitar top glued to the sides. There is a visible effect on the amplitude of the vibrating quadrants after the F-holes are introduced beyond the 3rd mode, revealing one theoretical effect of the Archtop sound holes. The first 3 modes are consistent with the fundamental eigenmodes of the steel string flat top acoustic guitar. The physics of the flat top steel string can be referenced in Trevor Gore and Gerard Gillet's Contemporary Acoustic Guitar Design, published in 2011. The first mode is referenced as the T11 monopole of the top plate. The second shape is a transversal flexural pattern, referenced the T21 cross dipole, followed by the longitudinal flexural pattern, or the T12 long dipole. Now we switch gears into the experimental analysis. Here we see a diagram of the experimental setup for a frequency sweep measurement technique used for FFT analysis. This technique was utilized in the acoustics lab at Indiana University, South Bend. A sinusoidal frequency sweep, 1 Hz to 3.125 kHz, is emitted from a signal generator and outputted to the emitting transducer. The transducer is attached to a stylus that contacts the sample at a desired location. As the frequency sweep excites the sample at explicit frequencies, a receiving transducer picks up the vibrations and sends corresponding voltages to a preamp, then into an oscilloscope. The oscilloscope is triggered by the signal generator. The sample rate of the oscilloscope is set to 6.25 kHz, resulting in a 3.125 kHz Nyquist frequency, which is the maximum frequency of the sinusoidal sweep. The sample rate is significant in capturing and analyzing the results without error due to aliasing. The signal is captured by the oscilloscope and inputted into MATLAB for analysis. Received signals of higher voltages corresponding to frequencies of the sinusoidal sweep translate to peaks on the FFT. These peaks are the resonant frequencies of the sample. For free plate measurements, a sample rate of 2.5 kHz was used, resulting in a 1.25 kHz Nyquist frequency. Here is the FFT plot for the first free plate sweep measurement. The first 5 fundamental eigenmodes are all below 200 Hz. The measured frequencies for the first 5 modes of the standard graduation top plate are 53 Hz, 89 Hz, 121 Hz, 145 Hz, and 173 Hz, respectively. Here we see animated renderings of the Fusion 360 finite element analysis for the standard graduation free plate. The fundamental 5 eigenmode shapes are in general agreement with Collin-Gauss violin plate modes FEA results. Again, the main difference being the aspect ratio of the respective plates and slight asymmetry of the cutaway. The black outline is the 0 position of the model. Chladni figure analysis is a technique dating back to the late 18th century. In modern times, a sample is inundated with a single frequency correlating to a peak on the FFT plot. Ground parsley was sprinkled evenly across the plate. As the excited plate vibrates, the parsley settles along the nodes and the eigenmode for a given eigenfrequency is revealed visually. This clip shows the first 5 eigenmode shapes of the Archtop free plate with standard graduation. The Chladni figures reveal the fundamental eigenmodes are most consistent with the Fusion 360 FEA results. This is the FFT plot for the free plate with F-hole perforations. The first 5 fundamental eigenfrequencies were measured at 45 Hz, 63 Hz, 118 Hz, 130 Hz, and 150 Hz respectively. the eigenfrequencies shift lower after the F-holes are cut out. This slide compares the finite element analysis results with the Chladni figure analysis for the Archtop top plate with F-holes. The order of eigenmodes is the same for the standard graduation free plate and after F-hole perforations. This is consistent with the Autodesk Fusion 360 finite element analysis results. For the final working step of the Archtop free plate, the X bracing is attached. Here we see the FFT plot for the free plate with bracing. The 5 fundamental eigenfrequencies were measured at 61 Hz, 92 Hz, 134 Hz, 150 Hz, and 178 Hz, respectively. With bracing, the fundamental eigenfrequencies shift higher. Here we have the rendered FEA animations for the free plate with bracing. It should be noted that the Chladni figure analysis was not performed for the braced free plate. The bracing interferes with the parsley and obstructs the Chladni patterns. The modeling shows the first 2 modes switch places. While it's possible for the order of the eigenmodes to shift due to different material properties of timber and other factors, that was not the case for this top. In my attempt to perform Chladni figures, the tails of the Chladni patterns were visible for the twisting and long bending modes. The bracing appears to have a great impact on the ring mode. The study now shifts to the Archtop guitar body or corpus. With the braced top plate attached to the sides and back, we see the lowest fundamental eigenmode is the breathing mode, or air resonance of the newly created cavity. Including this mode, the 5 fundamental eigenfrequencies of the Archtop guitar corpus are measured at 137 Hz, 221 Hz, 250 Hz, 281 Hz, and 315 Hz, correlating with the air resonance, the top T11, top T21, the back T11, and the top T12 modes, respectively. Next, we see an FFT plot of the guitar body with neck attached and hardware under string tension. The same 5 peaks corresponding to the fundamental eigenfrequencies were measured at 134 Hz, 221 Hz, 242 Hz, 263 Hz, and 297 Hz. The first 5 eigenfrequencies of the completed guitar shift lower with the added component coupling of the neck, hardware, and string tension. For this measurement, the guitar top is under 169 newtons of downward force due to string tension. This final FFT plot shows the completed Archtop guitar with a thin layer of nitrocellulose finish under string tension. The fundamental frequencies all shift higher, perhaps due to the slight additional stiffness of the added lacquer. The final frequencies are 138 Hz, 223 Hz, 248 Hz, 268 Hz, and 304 Hz. It is worth mentioning that these explicit frequencies are for this individual guitar. there are many variables that contribute to the final acoustic signature of an instrument. The effects of arch height, along with recurve thickness and geometry, and the material properties of the woods used cannot be overstated. The elastic properties of wood are heavily influenced by how well quartered the timber is milled. McIntyre and Woodhouse's publications titled On Measuring Wood Properties, Volumes 1 through 3, is a very enlightening study on wood's intrinsic properties. In terms of the material properties of the carved top plate, violin maker Martin Schlesky discusses in his work Speed of Sound and Damping of Spruce in Relation to the Direction of Grains and Rays, published by Cass, that cutting the longitudinal grain or radial rays, as is done when carving a top plate, affects the long grain and cross grain Young's modulus. This results in reduced stiffness and lower corresponding eigenfrequencies, which may account for some of the difference between the predicted frequencies and the FEA and experimental results. Taller arch profiles result in steeper cuts to the grain and rays, further reducing stiffness. With this understanding, Schlesky writes, the effects of the recurve is to decouple the plate as its own vibrating island of effective mass. This may be especially true for the archtop, considering it does not have a sound post to couple the top and back plates to each other. Now, let's take a look at the finite element analysis. The lowest resonance of the archtop guitar corpus is the breathing mode air resonance. This lowest fundamental eigenmode falls in line with both guitar and violin family research. The top and back plates vibrate opposite of each other, causing the breathing-like action of the guitar corpus. Here we have animations of this phenomenon rendered with Autodesk Fusion 360. First, the top, out, and in towards center, and the back, out, and in towards center. Here we have another Fusion 360 animation of the top plate and bracing with a pinned edge boundary condition. The pinned edge simulates the top glued to its sides. First, we have the T11 monopole mode, next, the T21 cross dipole, and finally, the T12 long dipole. The fourth measured FFT peak correlates to the fundamental T11 monopole of the backplate. Here we have the same modal shapes in order, rendered with COMSOL multiphysics. Comparison of the Chladni figure analysis with the FEA results rendered in Autodesk Fusion 360. The pinned edge model results were the same for both simulation softwares. We see the fundamental eigenmodes of the theoretical modeling agree with the experimental analysis. The violin measurement device created by Joseph Curtin and utilized by the Oberlin Acoustics workshop served as inspiration for this adapted guitar version. The ability to collect admittance and 360-degree near-field radiation measurements using an impulse hammer offers a clearer picture of how the archtop guitar projects sound in space. The frequency sweep technique utilized for this study is adequate to distill the eigenfrequencies and corresponding eigenmodes of the archtop guitar. However, The next chapter in Archtop guitar dynamics will be conducted using the established instrument acoustics techniques of the Oberlin workshop. The frequency sweep measurements were compared with both accelerometer and near-field radiation measurements. All three measurement techniques are consistent. Here we see the sweep measurement FFT of the completed guitar with finish under string tension. The 5 fundamental eigenfrequencies are circled. Next, we have the near-field radiation measurement FFT generated with the Beta Oberlin software. The reference microphone was placed directly in front of the bridge, and we see the same circled peaks for the radiation measurement. However, this is a logarithmic measurement along the frequency axis, but the values are the same. The top T11 monopole and T21 cross dipole contribute significantly to the near-field front. The air resonance, back T11 and top T12 long dipole contribute in near equal amounts to a lesser magnitude. We see the fundamental eigenfrequencies, and just beyond this fundamental hill, we see a secondary hill of frequencies waiting to be mapped. This is a modal analysis of the Archtop guitar top plate and body, which establishes only the fundamental eigenmodes and corresponding eigenfrequencies. More research is needed to continue bringing the physics of the Archtop guitar into focus. This study analyzed the fundamental plate and air resonance modes only. There is evidence of a low-frequency mode associated with the tailpiece that holds the strings opposite the nut. The guitar featured in this study has an X brace with cross braces along the top and bottom of the X. The Archtop guitar originally had a parallel bracing pattern, with both styles now common. This difference in bracing pattern may impact the fundamental eigenmodes. This study concludes that the Archtop guitar freeplate shares similarities to violin family freeplate dynamics. The fundamental eigenmode shapes agree with the eigenmode shapes of the violin freeplate up to F-hole perforations, the main difference being the aspect ratio and asymmetry of the guitar freeplate profile. According to the FEA results, the X bracing has an impact on the 5th modal shape, disrupting any ring mode pattern. Once the guitar plate is adhered to its sides, the fundamental eigenmodes agree with the dynamics of the steel string flat top guitar. The specific frequency range is different, and ongoing research of the effects of double F-holes on air resonant modes, along with a mapping of higher order resonant frequencies, will further reveal the Archtop guitar's unique acoustic signature and physical dynamics. Here we have a COMSOL multiphysics model of the Archtop guitar corpus suspended in a bubble of air. A paper published in 2015 titled The Evolution of Air Resonance Power Efficiency in the Violin and Its Ancestors by the Department of Engineering at MIT is the inspiration for the next steps in my research. I am currently working on a study to model the fluid dynamics of the Archtop guitar to gain better insight into the physics of the air resonant modes and effects of the double F-holes on the Archtop's acoustic signature. The F-holes are spaced further apart relative to the violin or cello, theoretically increasing their effects as independent sound holes. Other ongoing research includes conducting detailed radiation measurements of various Archtop guitars. Thank you for listening, and thank you to all the people and institutions that assisted in the pursuit of Archtop guitar dynamics. Stay tuned.